Okay, let's get started. Welcome to this session on validation of statistical software and self-validated ensemble models. Two of the talks are on the first half of that, and two of the talks are on the second. And each of those pairs of talks, the first one will be more on the theoretical side of things, and the second one will be an application of the method that they're using. And so I'm Tom Donnelly, and I'm the chair of this session. We're going to try to go about 25 minutes for the talks, 5 minutes for questions. Okay, and if you have a question, please raise your hand and let us run a microphone to you, because there are people watching this virtually and they just can't hear the questions. I can also repeat it if you'd like that, but we do want to try to capture all that information. And so if you have a question, please, we'll ask each speaker whether they want it at the end or if you want to be able to interrupt them. I just want to remind people as well, you heard that this is the 8th DataWorks. Well, there's a conference that preceded this that has since been absorbed into this. For about 20 years, it was the Army Conference on Applied Statistics. And for about 40 years before that, it was the Army Conference on Design of Experiments. And from that legacy, there is a Samuel Wilkes Award that will be given later at this conference. And we have one of the recipients of that here, Allison Wilson. If you don't know her, you should try to meet her. She's a wonderful person. And I think the last recipient may have been Rod Sturdivant, who I think was at West Point. So any of the Army folks will probably know who he is. But anyway, look forward to this year's winner. I think it's a well-deserved winner. So with that, let me introduce Ryan Lekivetz. He is the R&D manager for the Design of Experiments and Reliability Group at JUMP. And with that, I'll let you take over.
So thank you, Tom, and thank you all for joining me. So you'll see in the title here, I talk about the validation of statistical software. So kind of near and dear to my heart. And I'll really be focusing, though, from validation standpoint here, I'm going to be talking about testing statistical software, right, and how this relates to design of experiments. And one thing I'll say is that as a graduate student, at least in a statistics program, there was a lot of talk about developing R packages, developing applications, but I felt like I never had any idea about how to actually test those packages or how to test those applications. Right. And so in that sense, if we look at the outline here, so really we'll just start, what actually is software testing? Right, so what does it mean to test, especially statistical software? Really, what is the testing challenge? Right, so if you say, I do want to test my package, I want to test my software, how do I go about doing that? Then we're going to look at test selection as a design of experiments problem. Again, that's my background is in design of experiments. So that's kind of how I approach this problem, the testing problem. And for those of you who are familiar with this, then you're going to see this idea of covering arrays, which is going to be one of the proposed solutions that we have here. But so if you do a search for what is software testing, these are some common definitions that you'll see, right? To show the software works as intended, to ensure there are no bugs in the software, assures us the software does what it's supposed to do, right? That sounds like a reasonable way to talk about software testing. For our purposes of this talk, I'm going to say no, that's not what we're going to do here. So why? I mean, these all sound reasonable. I'll say there's kind of a psychological issue with these definitions, right? And these are telling us to show that the software works, which it's human nature to then tend to do that. You may not be sure what I mean, but let me just put it in a little bit simpler terms. So imagine if your colleague comes up to you, says, do you want to try out my new R package? If they say, can you check that this works versus try and break it, right? What do you think you're going to spend more time testing, or what are you going to do more with? If it's the first one, you may play around a little bit, say this looks reasonable to me. Whereas if you say try and break it, you're probably going to be a little bit more diligent into what you're doing. And the way I like to look at this too, if I ask a colleague, can you read over this email for me? There's a difference between does this make sense to you versus go through with your red pen and edit this as much as you can. So hopefully if that makes sense to you, this idea of let's try and break the software. So when we're talking about software testing in this talk, I'm going to use this definition from Glenford Myers in The Art of Software Testing. So testing is the process of executing a program with the intent of finding errors. So really that emphasis on with the intent of finding errors. So if I'm a test engineer, that is my goal, is to find those errors, is to break the software. Right? And this is quite relevant as well as oftentimes if you're developing an R package, well, who's the tester for that package? It's usually yourself, right? So when you're doing that, really you're trying to find those errors that you have in your code. But so the next natural question, if you can say, well, it makes sense that we want to try to break the software, we want to find the bugs. How do you go about doing that now, right? You can play with your software all that you want, try different values. Well, where do we look for them? Well, so Boris Beiser has a famous quote in the software engineering community. So bugs lurk in corners and congregated boundaries, right? So this is kind of telling us where should we start looking for these. And if we think about the boundaries, those make sense for if you have an if statement. What happens when one of your inputs starts going to 0 or starts going to infinity? Where do things start breaking down? Now, as statisticians, when I hear corners, that's what we think about as interactions, right? We have these different inputs to the system that when they work together, perhaps something bad is happening because the developer has forgotten to put in logic, one condition holds or something like that, right? So really these two slides kind of are formalizing what our whole point is here. So we're trying to break the software, and how are we going to try to go about doing that? Where are we going to look? So now if we think about the testing challenge then, right? So the next speaker we're going to have is a fresh test engineer. So imagine now you have a PhD in statistics. You've never really been told about testing software. So what is this testing challenge? Well, so the selection problem, right? How do you go to your boss and say, well, I did enough testing, right? So how do you actually go about selecting these test cases from this huge input test space to say that I've done enough? Which also relates to that quality problem. So if Yang, who's going to speak next, if she goes to her boss and says, well, I had 100 test cases, so hence I must be done. Is that going to fly? Well, how can you actually make an informed assertion that you've done enough testing, or that it's that it's ready for use or fitness for use, as it may be? And now I think something that often gets overlooked in the testing community for statistical software is really this idea of an oracle problem, right? And so I'm not going to dwell as much on this here, but how do you determine the expected behavior for each of your test cases? And so the reason I just want to say why it's perhaps doesn't get enough attention in the statistical community. So usually if you see this oracle problem, so the idea of the oracle is how do I determine, right? If I have my test case, how do I determine if a test outcome is what was expected, right? So if I put in some values into my software, it spits something out. How do I know that those values are correct, right? If I ask for a p-value, if it says 0.1, how do we know that that's right? And so I'll say, if you look at this discussion of statistical software, it's usually focused on numerical accuracy. So down to the 10th, 11th digits on some of the difficult problems. I'll say we often want to go further than this. So even for some general use cases, but I'll say the big thing here is how do we actually determine that expected outcome? And what does it mean if the results change? What if it just means that the algorithm actually improved, right? Maybe you spend some time improving the algorithm. So maybe those results are actually better, right? Are you just looking, do they change from one day to the next? Or what happens when something has changed within that software? But if you think about this from testing statistical software, well, okay, if the software crashes, if the software shuts down, that's a pretty obvious something went wrong. But what may be less obvious is something like timing. Okay? At what point do you say this is taking too long for what a user expects? Is it 10 seconds? Is it 15 seconds? Is it going for a walk for a cup of coffee before I say this may be a failure? Visualizations, right? So if you have a graph that's part of your output, how are you going to be able to validate and make sure that everything is being plotted correctly? A set of statistics, numerics, and so on. But one of my big points of that set of statistics and numerics, if you can't trust necessarily, from the test engineer's perspective, you have to go in under the assumption that you need to independently verify those numbers, right? So if there's no existing package that the test engineer can use, it's often the case that they kind of have to independently do those calculations and verify all of that. So if you imagine a single test case, you may spend hours trying to actually create your own functions in order to double check those values. Right? And so that's why it may seem that in this day and age with computers that it shouldn't take that long, right? If I have some test cases, I can go about creating an oracle very easily. So that's not really the case with statistical software. It depends on how deep you want to go to check, am I doing this correctly or not? Okay, so with that though, again, I think that there's probably, the oracle problem could probably warrant its own talk at some point. But so let's move on to the other two, right? So that selection problem and the quality problem. Right? And I'll say, so common techniques. So if you are doing this kind of testing, right? If you're creating your own R packages, R Shiny apps, anything like that. So the common techniques you've probably seen is so this repeated running of unit tests as a regression test suite. And so have you seen the definition of unit tests? So depending on where you go, where you look at the definition, the idea for a unit test is to focus on those smallest testable components or units before focusing on the overall system, before trying to look at a little bit more. And so the idea with the units, you may look at individual inputs. Let's make sure that these individual inputs are doing what they're supposed to do. And so the idea with the regression test, though, is I'm going to have the set of unit tests that every time there's a change, anytime anything happens, I'm going to rerun that set of tests to make sure things didn't break, to make sure everything is behaving as expected. And so I'll say this should absolutely be a tool in your tool chest if you're doing this kind of thing. But one thing I do want to point out is that if you think of the definition of unit testing, if you're familiar with design of experiments, that sounds an awful lot like a one factor at a time, right? Focus on just an individual unit. And if we think back to where do bugs lurk, if you're only looking at single units, those smallest units, we're not actually looking at any corners, right? All we're looking at are those boundaries. Right? And so that kind of leads us into this, well, how can we then think about that test selection problem as a design of experiments problem? Right? And so the idea here is that now that I have my set of inputs, let's think about all the things that we can test, right, for our piece of software. How are we going to test these effectively and efficiently? Now, one thing I'll say, this is where my typical background for design of experiments, I expect there to be noise in my response. Right? That's typically when I go about doing it. So here often, when you're thinking about setting up your test suite, you actually do want things to be deterministic, and that I don't want it to be that if I rerun my same test, one time it passes, one time it fails, then the issue is going to be you're going to be having to trace down what happened with all these different random seeds. How am I going to have to go about figuring out how to recreate that failure? Right? So oftentimes you may have stochastic components to it, but at the end of the day, you want to make sure that you can rerun that test the same way, so that if you have that oracle for pass and fail, that you can recreate that failure later on. One of the other differences here is that often in design of experiments, we're thinking of fitting a model. We have some underlying model that we're trying to fit. Here, we're really looking for fault detection, which is really, we're looking for those problems in our test suite. We're not necessarily fitting an underlying model. And at the end of the day, we may actually be happy. If we don't get any failures in our test suite, then we don't even really need to worry about trying to find those failures, other than perhaps improving our test suite later on. But so really then the question is, what does make a good design or a good test suite, right? So I said you should be starting with this idea of unit testing, regression unit test suite. But let's say if we want to go further, right? You feel comfortable with that. So what is going to make a good design? And so let's recall that bugs lurk in corners and congregated boundaries, right? So it makes sense if you've got your boundaries set up, you figured out those places where you should look. How can we now start looking in the corners? Well, so this sounds a lot to me, at least again, coming from a design of experiments background. If you've taken a design of experiments course, or if you're doing, fitting a linear model for a design of experiments problem, you may have seen these fundamental principles of factorial effects, right? So effect hierarchy, which just says the lower order effects are more likely to be important than the higher order effects. She just says, well, I'm going to look at my main effects first. Then the next batch of effects I might look at are the two-factor interactions followed by the three-factor interactions, etc. And I mean, and there's empirical evidence to suggest that in general, that effect hierarchy holds. Effect sparsity, again, if I'm in the linear model world, so oftentimes if I'm using a designed experiment, I don't want there to be that many important effects. If every single effect in that model is important, it's going to be hard to really do much with figuring out, well, what's driving this system. And if everything does, that's great. But I'll say oftentimes if we're talking about doing a screening experiment, for instance, we're trying to figure out what things are most important. And just the heredity, this depends on who you are. You may disagree with this one, but that just has to do with the interaction being significant only if one of the parent effects are. So again, just at the bottom here, you said, well, so what if we actually think of these failure-inducing combinations? So I said, here we don't have an underlying model, but let's say if I wanted to test software, and my interest is in figuring out where these bugs are, right? I want to look at the corners, I want to look at the boundaries. So what if we think about designing our test suite to look for these? So let's just do the same thing for combinations instead of effects, right? So the combination hierarchy would say, well, what's going to be the most likely case where there's going to be problems? Well, even if you think of your own coding, it's most likely I forgot some problem with my if statement or an extra if statement within that, right? So this combination hierarchy, we just say it's kind of that KISS principle, right? I'm going to look at the simplest explanation. That's probably going to be the first place to start looking if I have a failure. Now that combination sparsity, this number of failure-inducing combinations being small, this depends on if you have ever done this type of testing before. And I will say what may happen is that if you're moving from doing the simple unit testing, those single factors, if you move into this kind of approach, that combination sparsity may not be correct. You may find a failure on every single test that you run. And so sometimes you got to get your things in order before this is really going to have a much bigger impact. And I'll say, so the idea of heredity, this is actually something that our test engineers do intuitively, right? So if you think of something like a test suite, if you were to say, well, here's a failure, let's try to figure out what the underlying cause is. Well, so a combination is more likely failure-inducing if at least one of the parent factors involving the interaction is known to be more likely failure-inducing. So it sounds really wordy, but so let's just say if you just added a new feature to your software, anything involving that new feature is a lot more likely to have bugs in it than something that's existed for 20 or 30 years, right? And so that's all that this is really saying, is that there's going to be those certain inputs that test engineers know are more likely to are going to have problems. And so that idea of heredity comes into play there. Well, so you may say, well, that just sounds great. I can talk about those principles all I want. But it turns out there's empirical evidence that these hold up, right? And so here's if you look at the left-hand side of this table, that's the number of factors involved in failures of some different software systems. So you can look, by the time you look at your two-way combinations, for something like medical devices, 97% of the failures have been identified just if you can look at those different pairwise combinations. And if you think as you start increasing the number of factors, there's a lot more 3- and 4-way combinations, right? So in some sense, by focusing on, let's say, these 2- or 3-way interactions, you can be pretty confident that you found a lot of your failures or a lot of your bugs just by focusing on that. And so this gets us into this idea of combinatorial testing, right? So if you're ready to move beyond that idea of just the simple unit tests, so this idea of combinatorial unit tests are really just this family of test case selection strategies. And I talked about that idea of a covering array. So all that a covering array is, a strength T covering array says that if I take any set of T inputs, right, all possible combinations of those T inputs occur at least somewhere within the test suite, right? It doesn't say how many times, it just says it occurs at least once. So why is that nice? Well, if you think about this idea of a covering array, if I could create such a test suite, this kind of solves the selection problem and the quality problem, all right, from that test engineer's perspective. So this gives a test engineer a way to select those cases, right? This tells if you're using the covering array, now you've been able to cover all of these 2- or 3-way combinations somewhere within your test suite. And what's more, so now when Yang goes to her boss, she can say, well, look, I've tested all combinations up to 2 or all combinations up to 3-way combinations have been tested somewhere within my test suite. So when the software is ready to ship, if she can say, well, it doesn't look like we have any failures due to 2- or 3-way combinations, then she can feel a lot better signing off on that, saying the fitness for use is there when it's ready to go out. And again, just that idea, this moves beyond that one factor at a time. And again, just to point out, so, if you're familiar with the design of experiments literature, the definition of a covering array just said that every possible combination occurs at least once, right? And so that sounds very similar to the definition of an orthogonal array, which just says every possible combination occurs the same number of times, right? So it doesn't seem like there should be that much of a difference. Well, so if you look at this table at the bottom, you don't have to pay too much attention to it, but all I want to say is the bottom row there has to do with the number of binary inputs. So let's just think of if we just had checkboxes, right? In a covering array, a binary covering array of strength 2, so all possible pairwise combinations, you can do 1,716 binary inputs in just 14 runs for a covering array. Right? If you were to do the same thing for an orthogonal array, you're looking at about 1,720 to get the same thing. There's a huge difference. Now again, but don't forget, the orthogonal array wants to make sure everything occurs equally often. All we care about in our test suite is just that it occurs once. Right? So that's very cost effective, which from the test engineer's perspective, again, once you can get to the point that everything passes, you're able to say a lot. Here's just a couple of examples. So on your left, so there's a covering array, so with 6 runs, 5 binary inputs. And so all that I want to point out here, if you take a look at any 2 columns in here, the combinations 1, 1, 1, 2, 2, 1, 2, 2 occur somewhere within there. Right? And it turns out the one on the left is optimal, and that you can't actually find a smaller covering array than that. Now the one on the right is a strength 3, which means that now if I take any triplet, take any 3 columns in there, all 8 combinations occur somewhere within that test suite. Now it also turns out, though, that one's not optimal. And so if you look in the covering array literature, though, there's a lot of time spent on trying to find those optimal covering arrays, right? So trying to find a smaller design than what's currently out there is where a lot of the research is. But just in the interest of time here, just want to make sure there's a little bit of time for questions at the end. I just want to say, so why covering arrays? Really, they are cost efficient, right? If we go back to that orthogonal array one, right? If you think of over 1,000 binary inputs, if I can get by with a 13 or 14 run test suite and say that I've covered all pairwise combinations, that's very empowering to a test engineer to be able to say, I've been able to test all of these pairwise combinations and I didn't find any failures. Again, it solves that selection problem as to what to test and really treating this as a design of experiments problem. It helps with that quality problem. And again, going back to that, if all the tests pass, well, now you can ascertain there are no faults due to those T-way combinations. It really is a disciplined approach to testing. It helps that test engineer being able to set those up. Now, again, that's not to say it's going to solve all your problems. This should just be viewed as another tool in the tool chest, right? And really, this also goes back to when do the combination sparsity and hierarchy hold? Again, the first time you try this out, you may find a lot more failures than you care for, and you can spend a lot of time trying to chase down all of those different failures. And just depending on the literature that you're in, so this idea of covering arrays to the system under test. I think in the interest, because we started a minute or two late. So just some other considerations. One of the biggest problems is the fault localization problem. So let's say if you've decided that you do want to use covering arrays, what happens when you actually do find a failure? Because they're so cost effective, it also turns out that you may have a whole bunch of causes to go through, right? So now that you actually do find a failure, you may have this large list of potential causes, all of these different pairwise combinations that you have to go through and figure out which of these are the real underlying cause, which actually goes back to that idea of the heredity one, where oftentimes what a test engineer will do will say, well, based on the nature of this failure, I kind of already know where to start looking. Which also goes into things like locating and detecting arrays, which actually help pinpoint what those are. Constraints, not surprisingly, sometimes some inputs don't work in conjunction with others. Just some other comments. They're random seeds to really make sure that you keep them. I think it's happened to almost every test engineer at least once. They don't keep their random seeds. And it takes them days to recreate a failure that they found on one particular test instance. You're going to see this idea of data set generation show up in the next talk. And just to say, there is software out there. So, I mean, we do have it in Jump Pro, but also Axe is out there that's free. So, I mean, through NIST out there as well. So, I mean, it is possible to be doing these now. And just, I know I'm pretty much out of time. I want to leave some time for questions. I just want to show really quickly, though, if you go look at the slides that should be posted, we have an example here with XGBoost, right? So imagine now somebody's created a Shiny app, their own application for some GUI for XGBoost, and they say, well, do you want to go ahead and test this for me, right? You look, that's a lot of different inputs in there. So I think here, in this example, for instance, we had 34 different inputs for XGBoost. In some of these continuous, you might want to use at 3 levels. If you think of those boundaries, you might have a middle point, a low, and a high. So just to point out, if you look at that top number, if you look at the input space, and this was even making those continuous ones, which are actually infinite, into 3. Good luck trying to test that, the full factorial on that. But see, if you think of this, a strength 2 covering array, you can actually construct that in 25 runs for the XGBoost GUI. Right? And on top of that, that 3-way coverage, so not only does that have all pairwise combinations, you're at about 72% for the 3-way combinations. So with that, I'll stop there and if we have any questions. Thank you.
Okay. There are no questions in the chat, but in the room, I think we have time for at least 1 or 2 questions. Does anybody have any for Ryan? I'm not seeing that. Oh, we have one in the back.
Yeah.
Oh, thank you. So yesterday I was in the machine learning workshop, and one of the last things that we talked about was reinforcement learning. And one of the topics that came up is that when one of these machine learning algorithms is playing a game, sometimes it can find a bug in the code just by random chance.
Yeah.
So do you see any role for that kind of algorithm in software testing in the near future, or maybe not?
So absolutely. I mean, I think, and that's where, even at times with another tool in the tool chest, I think sometimes these can also be worked in conjunction with each other. So one of the things is when you have some of those levels for your inputs, that's where it is helpful at times to have those random components in there, right? So if you think of the reinforcement learning, sometimes as well, though, maybe you can guide it to say, for one of these levels, stay within these boundaries. I want you to be choosing random values within here, but stay within some of these boundaries to make it more dead. And so I think it'll have a similar effect, but in some sense, you can make sure that you've covered some of those corners that it may not otherwise. Yeah.
Okay, I just wanted to make one comment here. Jump practice is what it preaches here. One of the things as an engineer, I get to download yesterday's build of the software. So every night, Jump runs thousands of tests on all the code they changed yesterday. And I think of this with respect to all the agile systems in DoD where there's constant software development. Okay, we're always trying to spin out a new upgrade in the software to our systems. And I think that's the opportunity here to put this type of testing in so that we are consistently checking for, the bugs that we might be creating in this, constantly updating environment. So with that, if we want to thank Ryan one more time, we'll get our next speaker up.